Everybody, and welcome to exercise 1 on page 98. And this is an exercise just to explore some rings and to see if you can explore some of the properties that they have. Okay, what we're going to do in this video is to start this exercise out together, just to pick a couple of parts of this, do it together so you can kind of get an idea how this works, and then I'm going to ask you to finish the rest of this exercise on your own. Okay, so let's first read what they're asking us to do here. So each of the following sets is a ring under the indicated operations. We don't need to verify that, we're given it. And they'd like us to provide the additional requested information in the spaces below. They're going to ask us about some properties that the ring might have. All right, so let's do part A together here first. All right, so they give us the set of integers, okay, with the operations of integer addition and multiplication. We know that that's a ring. Okay, and first thing they ask us is whether it's a commutative ring. Okay, and let's recall what that means. When we say that a ring is commutative, what we mean is that the multiplication operation is commutative. All right, so what do you think? Is multiplication commutative in the integers? Is m times n always equal to n times n? N times m? Sure it is. Okay, so z, set of integers, is a commutative ring. Okay, next question, does it have a unity? Okay, it does. Okay, a unity again is just is an inverse under multiplication. Okay, and so the number 1 has the property that if we multiply it by any other integer, we're going to get that same integer back again. Okay, and then we move on to the question of zero divisors. Does the ring Z have any zero divisors in it? Okay, well, let's think about what a zero divisor was again. Okay, so zero divisors are non-zero numbers that you can multiply together that would give you 0 in the ring. So is it ever possible to take two non-zero integers, m and n, multiply them together and get 0? That's never going to happen. In other words, if ordinary integers multiply to 0, then we know that either m equals 0 or n equals 0. Okay, that tells us that there are no zero divisors in this ring. Okay, and then we come to the question, is the ring of integers an integral domain? Okay, well, what properties did an integral domain have to have again? Really 3 of them. It had to be a commutative ring with unity that has no zero divisors. And notice that Z has all 3 of those properties. Okay, and so therefore Z has to be an integral domain. Okay, and then the last question they'd like us to answer is, what about units? Okay, what are the units in this ring? Okay, well, here we have to recall from the last chapter what the definition of a unit is. Okay, so a unit is just an element in the ring that has an inverse under multiplication. Okay, are there any elements like that? Okay, in the ring of integers? 1 would be an example. Okay, because 1 times 1 gives us the unity. Okay, 1 times 1 is itself. Okay, can you think of any other element in the ring of integers that has a multiplicative inverse? I can think of one other example, and that's -1. Okay, and if you wanted to convince me that -1 has an inverse under multiplication, you'd have to tell me what goes here. What can we multiply by -1 to get back to the unity element? Well, we can multiply it by itself. Okay, so since -1 times itself gives us the unity, that means that -1 is also a unit in our ring. Okay, now do you agree that those are all of the units, that 1 and -1 are the only 2? Okay, well, maybe just to play a little bit here and convince yourself, take something else like 3. Is it possible to multiply 3 by something and get the unity element? Okay, well, you might look at that and say, I can multiply 3 by 1/3 and get 1. That's a true statement, but is 1/3 an element of our set? No, 1/3 is not an integer, and so there's no integer that we can multiply 3 by to get 1. That's the reason why 3 is not a unit in this ring. Okay, so I think we've completed this process for part A. I'd like to do one more part of this together. Okay, let's scroll down and look at part C here. Okay, so this time they'd like us to look at the set Zn, okay, where n is not a prime number. Okay, and this time our operations are addition and multiplication modulo n. Okay, so first question, is that a commutative ring? Okay, it is, because we're talking about multiplication modulo n. Doesn't matter what order we multiply integers modulo n, and we're going to get the same thing. Okay, and we do have a unity element. Okay, the number 1 again, that's going to be an element of the set Zn. Okay, and then we come to the question of zero divisors. Okay, now I'd like to explore this with a couple of examples. Okay, so I'm going to flip pages on you here. Just go to a blank page here, and we'll look at a couple of examples. Okay, maybe starting with the number 6. Okay, remember how we said we want n to not be prime. 6 is not prime, okay, because we can break it down into 2 times 3. And notice that in Z6, 2 times 3 is equal to 0, okay, because after all, 6 breaks down into 2 times 3, so 6 mod 6 is 0, and that implies that 2 and 3 are zero divisors. Okay, they're non-zero numbers that we can multiply together that happen to give us 0 in the ring Z6. Okay, let's take another example. What would be another example of an n that's not prime? How about 10? Okay, that's not prime because we can break it into 2 times 5, but that calculation means that in Z10, 2 times 5 is equal to 0. So 2 and 5 are zero divisors. Okay, and so what I hope you're seeing here is that for any n that's not prime, you can always do this. You can take that n, you can break it into 2 pieces, and you get zero divisors as a result of having those 2 pieces. Okay, so in general, what we can say is that if n is not prime, that implies that n is going to be equal to ab for some a and b in Zn, and that implies that a and b are zero divisors. Okay, so what we've learned then is that if n is not prime, Zn will always have zero divisors. Okay, and don't forget, we're assuming that n is not prime. Everything that we're saying here is under that assumption. Okay, and so now, what do you think about the integral domain? Is Zn an integral domain? Well, the answer to that has to be no, because of the fact that we have zero divisors. Okay, one of the properties that we need to call something an integral domain is it's not allowed to have any zero divisors. Okay, so that's another conclusion that we can draw. Okay, and then finally, what would the units in this ring Zn be? Okay, and again, the units are the numbers that have inverses under multiplication. What's interesting is you've already answered this question in a previous homework exercise in this course. The elements in Zn that have I can't say that word, inverses under multiplication are the ones that are relatively prime with n. Okay, and in fact, you have notation for that, u of n. You might remember this as a group that you studied earlier in the course. The set of all integers between 1 and n minus 1 that are relatively prime with n, those are exactly the units in this ring Zn, as it turns out. Okay, So I'd like you to try the rest of these exercises. You're going to go through a couple more examples of rings and see if you can give answers to questions as to which of these properties they have.